Okay, let's get this rolling. Good morning. We're going to do this a little bit differently today. I didn't put up the outline slides, right? Some of you may have noticed. We're going to do this all written out because today is, you can cue the groans, going to be focused on the derivation of the heat equation. Okay, yeah. So that is a big old, and let's derivation of the heat equation. We're going to go through this process once because the heat equation is going to take up approximately a third of our class. All right, this is the governing equation for all things heat, conduction and diffusion related. All right, it's one of the most important equations in science and engineering because it describes, as the name implies, things like the spreading of heat by conduction, but also things like the way that contaminants spread in bodies of water or in, a gas or pollution in air spreads throughout a quiescent room. So the applications go beyond the boundaries of heat transfer. And it's also a really simple equation to derive. Okay, so this is not going to be terribly painful. All right, so at the conclusion of the last couple lectures, right, we left off with Fourier's law, which governs all things, or which is governs the heat rate, right, for conduction. Given by, so the heat flux, right, being equal to negative K times grad T. And then the heat rate being the surface integral of the heat flux. Okay. So using this, right, the idea is if you know the temperature distribution, you can find grad T and you can figure out the heat flux and you've got your problem solved. Okay, it's just a matter of taking partial derivatives. So the paradigm here is known T, X, Y, Z, T. Apply Fourier's law and you get out your heat flux. Well, we're going to be, right, this begs the question then, what if we don't know the temperature distribution a priori, right? We march into a problem, it's very rare that we have a perfect functional description of the temperature throughout a three-dimensional domain in time, or even a one-dimensional domain in time, right? More often, you are able to measure the temperature at a couple of points, or measure the heat transfer at a couple of points, and you have to fill in the blanks. And so the heat equation is going to give us the tools to take that that knowledge about a few different places or a few different instants in time and turn that into a theoretical description of the way that heat or temperature evolves inside of solids or fluids at rest. Okay. So the overarching goal of this derivation is going to be derive the equation that governs T in space and time. So to kind of get everyone oriented, the general process we're going to be following, broad strokes here, kind of flow chart. We're going to go ahead and start out with a really tiny control volume or system. And we're going to go ahead and apply conservation of thermal plus mechanical energy. Right, so this is one of those versions of the first law that we spent time in chapter 1 covering. And we're going to go ahead and throw in, right, this thing we know about the way that heat flux occurs with Fourier's law. These two things are going to be combined with a first-order Taylor series to approximate say nearby values, and what we'll get out is finally the heat equation. So really only a couple of steps here, and we're not going to be opening up any new real material. It's just going to be applications of things that we've seen already, and I'll remind you guys of what Taylor series is when we get to that point. Okay. So proceeding with the derivation, we've got, let's consider first a small volume, which will be considered a closed system. Okay, no mass entering or leaving. Yeah.
What's that? Is it nearly values?
Oh, nearby values. Sorry.
Nearby.
I'll slow down a little bit. So we get nearby. Okay. So start out. We're considering this some small volume that has no mass entering or leaving it. Okay, which defines it as a closed system. So. We'll go ahead and draw our control volume around that system, okay? And we'll let this thing be, it'll be, you have dimensions of delta x by delta y, and then it'll be some delta z into the page. Right, which means the thing has a volume of delta x, delta y, delta z, and the sort of the face, the areas of each face can be, found as either delta x, delta y, or delta y, delta z, whatever the relevant dimensions are. Okay, so if we go ahead and apply our first law, right, our energy balance that we spent last, week and change talking about, we write that as E dot stored, right? This is the familiar E in minus E out plus E dot G, where once again this is sum of all thermal and mechanical energy stored inside of the volume. E in and E out are the thermal and mechanical energy respectively entering and leaving by heat transfer and or mechanical work, and then E dot G is the generation of heat or thermal energy, or the conversion of types of energy that are not thermal or mechanical into thermal or mechanical, like by chemical reaction or heating up of an electrical element. Okay, and so to remind you guys, right, we've got two sort of different types of terms here. These E in and E out, these are, right, we said before, these are called surface terms. And the E stored and E generation are known as volumetric terms, because the E in and E out, that energy has to go through the surfaces of our, it has to go through this red-dotted surface of our system, whereas the other items are somehow tied to the amount of matter within. Okay, they're generated inside of that system. So we're going to go ahead and make a couple of assumptions here. The first is going to be assume no mechanical work. What does that do for us? It means that our E in and E out terms are due only to heat transfer. Okay, so this turns into E dot stored is equal to Q in minus Q out plus EG. Right, we're going to assume that our system here is stationary, meaning there's no bulk motion of the matter inside of it, and that there's no phase change occurring. So this could just be a block of solid matter, or a volume of stationary gas or liquid. No bulk motion, no phase change. And what this does is it means that all of that there's no mechanical energy involved in E stored, so it's only thermal energy, and all of that thermal energy is the thing we call sensible energy. There's no latent heat involved. So this turns into this E dot stored term becomes rho C V T dt equal to Q in Q out plus E dot G, where this right here is the rate of change of sensible thermal energy. Okay. So we're going to go ahead and consider the case first. We're going to do this in one dimension, and we'll just say the process that we follow for the one-dimensional derivation applies to the other two dimensions, and we'll generalize from there. So I'm going to go ahead and redraw this system here. For the 1D case, means that there is heat transfer occurring only in the x direction. Which means that t is a function of just x and time, where big T is our temperature again. Okay. So let's go ahead and define this thing. So here's our x coordinate. Go ahead and say that this side is at x equals 0. This side is at x equals delta x, right? We've already established the width of this thing is delta x. We've got Q in. We have Q out. We have we'll go ahead and just draw this energy generation term, and then we have also stored energy stored. So our what does our Q in term consist of in this case, right? Q in is essentially equal to Q double prime x times the area of that face that it's crossing, or Q double prime x times delta y delta z. Right? Included in this, or rather, sorry, this is, yep. So we've got our right, this is the heat flux in the x direction at this point, multiplied by the surface area of that face. We have our EG term right? We're going to go ahead and introduce a new nomenclature here. We'll say this is sum product Q dot times delta X, delta Y, delta Z, right? It's essentially saying is this is the amount of heat generation per unit volume, and here's the volume of this tiny little control volume, all right? Our E stored, we've already said it's going to be rho V, or rho C, delta X, delta Y, delta Z, times the time rate of change of the temperature of that solid. And finally, Q out is equal to Q double prime X plus delta X times delta Y delta Z. This is really the only term that's going to throw us the curveball, right? This X plus delta X. Because what this is saying is that the heat flux at this point is not necessarily the same as the heat flux at this point. Okay? So we're referring to this one as just, Q double prime sub X. And over here we're saying it's something close but slightly different. It's been incremented by some amount. And so if we go ahead and sub in, let's first, we're going to now use a Taylor series to approximate Q double prime X plus delta X. And what Taylor series says is that if we're taking a nearby point, right, in this case, we're saying that the heat flux at X plus delta X is related to the heat flux at X, but plus partial Q X partial X times delta X plus 1/2 partial squared QX partial X squared delta X squared plus, right, 1/3 dot dot dot. This is the infinite series that we use to approximate a function when we, to approximate a function by the value at a nearby point, right? So we're going to go ahead and use just this first term here, or these first two terms, I should say, which are known as a first order Taylor series. Okay, and we're going to drop everything else. The idea being that if we start to allow this little chunk of matter to get smaller and smaller and smaller, right, this delta X is going to get really small. All these, there's going to be a delta X squared here, a delta X cubed, a delta X to the fourth. All of those higher order terms, okay, are going to get really, really small as delta X, approaches 0. And so we're going to go ahead and chop it up here and say that these are the only ones that are large enough for us to worry about for this problem. So if we go ahead and plug these into our energy balance, okay, E dot stored equal E dot in minus E dot out plus E dot G. This turns into rho C delta X delta Y delta Z dt is equal to Qx double prime delta Y delta Z minus Q double prime X plus D Q double prime X dx Z plus Q dot delta X delta Y delta Z. All right. So we've just taken those right, those expressions with the substitution made for this first order Taylor series substitution made for our Q out term, all right, and plugged them in. So a couple things here. Now, because we essentially have if you look at this, we've got a Q sub x double prime, delta y delta z. We've got a Q sub x double prime, delta y delta z over here. These guys are going to cancel each other out. So these cancel. All right, I'm going to go ahead and move this up. Those guys cancel. And what we're left with then is rho c, delta x, delta y, delta z, partial t equal to prime y and delta z. So the next, or I should say our last step here, is just going to be recognizing we have this delta x, delta y, delta z term throughout. We're going to again cancel that all out. So divide through by the volume, delta x, delta y, delta z, and what we end up with is rho c partial t equal to negative x plus q dot. Okay, I lied. There's one more step here. We've got a T here, right? Temperature. This is the language we want to speak. It's temperature. We have a heat flux here. We also have this thing called Fourier's law that we can use to relate these two to one another. So if we go ahead and plug in, right, Fourier's law in 1D says that q double prime x is equal to negative k partial t partial x. If we go ahead and just substitute that expression in there, then we end up with rho c, time rate of change of temperature, is equal to k partial x, sorry, that's k partial x k dt dx plus q prime. Okay, so this is right here. This is the most general form of the one-dimensional heat equation. In this class and in most applications, we also make the assumption that our material is homogeneous. Okay. In other words, we make the assumption that the thermal conductivity, which is a property of the material itself, does not change throughout the material. Okay. Which is usually a pretty good approximation if you're dealing with a block of metal or a volume of fluid or something. Which means that this k, if it doesn't vary in x, can move outside of this derivative, and we get rho c t is equal to k second partial derivative of t plus q dot. And this is the heat equation. Which is a very big deal in, as I said, all of science and engineering. So it's pretty simple to deal with, right? There's nothing super complicated looking about it, and the way we got here was actually a fairly intuitive process. So I'm not going to write this down, but I want to spend just a couple of or just a minute here, sort of contemplating, right? I want to review the physical reasoning that led us here, because this is going to be really helpful when it comes time to interpret and solve problems. So what law of thermo is this expressing? Well, there's a component. It's actually both, right? We have our Fourier's law, right, which is essentially an embodiment of the second law of thermo, saying that heat transfer has to occur in a direction of decreasing temperature. Okay, that's where that Q heat flux comes from. But the entire thing is just a reworked version of conservation of energy. It's just the first law with some substitutions made in, right, for a small volume. All right, in a more mathematical bent, what kind of equation is this, and what sort of what will its solution actually give us? Right. So we've got a derivative on time of our temperature and a derivative on space of temperature. Since we have these mixed things, right, derivative by time and by x, this is what we call a partial differential equation. And the solution should then give us t as a function of both x and time. So, you know what? I'm going to write down kind of the SparkNotes version of this. This is a reworked version of Thermo law number 1. Is a partial differential equation with solution t, x, and time. And then the terms in this equation represent familiar concepts. Which are this rho c partial t, okay? What sort of physical effect does this represent in terms of our first law? Remember, this is the rate of change of stored thermal energy. If rate so it's related to that E stored. Okay. This K d squared T dx. There we go. This K d squared T dx squared is the net rate of heat transfer by conduction into our volume. So this is heat transfer into system by conduction. And so in our original heat balance, this is essentially the E dot in minus the E dot out. It's all wrapped up into that term. And then finally, the Q dot, right? Our Q dot is the rate at which our other energy box turns into thermal energy inside the volume. And so this is related to our E sub G term. Okay. The one difference here is that all of these are per unit volume because we went through and we divided by that delta X, delta Y, delta C. Okay. So this is our one-dimensional heat equation. The exact same reasoning applies to the heat flux in Y and in Z. Okay, we're not going to derive those, but we'll just go ahead and write out the three-dimensional form, and it should hopefully see the relationship between the two. So, you guys, all right if I go and scroll down? Okay. So the 3D heat equation essentially comes from the same thing. The way we write this is rho c T dt is equal to K squared T x squared plus K squared T delta y squared plus K delta squared T and delta or partial z squared plus q dot. Okay, so it hasn't made it that much harder. The only thing is now we've included these partial derivatives on y and z. And so just like this one represented the net amount of heat entering the system boundaries along, by heat conduction along the x-axis. Sorry, those second two represent the amount of heat conduction into the system along the y and z axes. Right. So those still go into your E dot in minus E dot out terms in your energy balance. If we go ahead and factor out this K, right, our thermal conductivity, then we can write this in the more compact form. Partial T is equal to K del squared T plus Q dot. And this is the 3D heat equation, which is an even bigger deal than the one-dimensional version. Okay. Write that more. Okay. If we do, yeah.
So you said that this is only for small volumes. How does this apply to large volumes?
Well, the idea is kind of the mental jump we have to make is we say if we make our volume smaller and smaller and smaller and smaller, eventually it'll become a point in space. Okay, this is the same approach that underlies all of calculus, really. So if we allow that delta x, delta y, delta z to become, take the limit as they go to 0, then this becomes valid at every single point throughout a volume because it essentially individually governs each one of the points that make up a continuum of matter. All right, which is why you go from this discrete volume now, we were able to divide that out, and we now have this continuous equation that applies everywhere inside of any volume, right? Because it applies at each point independently. So now we've gone from this system control volume approach to differential equation approach. Okay, so instead of this discrete chunk of matter, continuous governing equation. So if we solved this, right, it's still if we solve this partial differential equation, we're still essentially it's motivated by this conservation of energy in a small volume, but what we get out is the temperature distribution as a continuous function. Okay. So if we divide through now by the product of density and our specific heat capacity, okay, then we can just rewrite this in a equivalent but more compact form of alpha delta T plus 1 over rho C Q dot, where that alpha is known as the thermal diffusivity. Spelled it right? Yes. Which has units of meters squared per second. So this is another common property that you'll see for materials. And so the reason for expressing it, this equivalent version is just if you have a table of thermal diffusivities, instead of a table that lists each of these products or these quantities independently, it's just another option for how you inject your material properties into the mathematical problem. So at this point we're done deriving the heat equation. That's it. The rest of the first third of this course is going to be dedicated to how to solve it, because partial differential equations are some tricky creatures, and there are a lot of tricks that we can use to tackle it. So yeah.
What happened to delta squared?
Sorry, I just omitted that square right there. So before we get into solving, there's one other concept that we need to cover, which is that of boundary equation or boundary conditions. Sorry. So the heat equation we've established is a partial differential equation, or in mathematical parlance, a PDE. Okay. It's a second order differential equation on x, y, and z. Okay. So it has second partial derivatives on all the spatial coordinates. And if we were to forget about time, okay, if you had an equation that just said d squared, f dx squared is equal to 0, if you solve for f by integrating, right, how many extra conditions do you need to know in order to fully constrain the problem? 2, right? Because you're going to have 2 constants of integration. Same thing applies here. Second order on x, y, z means that we need 2 boundary conditions, that is 2 pieces of information about the edges of the xyz domain for each coordinate. So this is where I mentioned, when we're actually doing in the physical world, we can't usually measure the temperature throughout the interior of a solid object or of a fluid. But what we can do is measure it at specific points. And so, if we're trying to blend theory and practice here, boundary conditions are easy things to get from measurements, because you can measure the temperature at the edge of an object, for example, then use the heat equation to fill in the rest. Is also a first order equation on time, which means that we need 1 initial condition. That is, we do need to know how the entire volume is behaving at some instant before, at the beginning of the evolution of the conduction that occurs. Okay. For certainly in the next chapter, we're going to be limiting ourselves to steady state conduction, which means that partial t that time rate of change of temperature is going to go to 0, which gets rid of this first order on time and gets rid of our requirement for initial conditions. So we'll tackle this initial conditions thing, I think in chapter 4 or 5, when we get into transient conduction. So we have some classic boundary conditions that you will generally, classic and common boundary conditions. That we will often see used to describe physical systems. So the first of these is a temperature condition. And what this is essentially, it's if you have a specific or a specified constant temperature at some location on the boundary. So an example could be, you could say that T is equal to 0 at x equals L. Or T equals 3 at x equals 0, right? It's a known temperature at a known location. We also have a flux condition, which is a specified heat flux at a location. So in this case, this could mean essentially Q double prime x, equals 0 at x equals, I don't know, 5 meters or something. But right, we can plug in Fourier's law here for that Q double prime. We could say instead that this could be restated as negative k dt dx is equal to 0 at x equals 5 meters. So those would be equivalent statements, which is why we can use this as a boundary condition for T, okay? Because it's some piece of information about the way the temperature is behaving at the boundary. We could also, it doesn't have to be in the x direction. It could be negative k, partial t, partial y is equal to, 5 watts per meter squared at y equals L. The idea here is any combination of known constant heat flux and known location. And then finally we have the convection condition. And this is one that we see a lot in practice because, let's say we are, I used this example before about like the cooling of consumer electronics. Okay, if we have something that describes the way that, or the heat equation can be used to calculate the way that heat travels through a heat sink that's embedded in the back of a phone. All right, but what is happening to that thermal energy once it reaches the back of the phone is in contact with air. Right? There's this convective cooling at that point, right? Or that's the case with really almost any sort of heat sink, is that it travels throughout the solid according to the heat equation by conduction, and then gets dissipated from there using convective cooling. And so in this case, this is a version of the heat flux, but it's a heat flux that depends on the convection rate at the boundary. So, in other words, Q double prime x or Q double prime, normal to the boundary, has to be equal to Q prime convection. So plugging in our rate equations for both of these, we can say then that's negative k dt, dn is equal to h t surface minus t infinity. So I've gone ahead and written this in terms of partial t partial n, because whatever coordinate system we're working in, this has to be the heat flux through that surface. So if we're talking about one-dimensional heat transfer, okay, if we're working just in our x coordinate, like that first version of the heat equation that we derived, our boundary conditions are just going to be on x. All right, so in that case, n would be replaced with the coordinate direction normal to the surface we're considering. The idea here is that as the surface, like if this is an evolving temperature field, say the thing starts out at some temperature. Okay, you heat up a block of metal in your oven, and for some reason, you set it out to cool, like any good metal baker would. What's going to occur is that as the thermal energy is dissipated away by convection, your surface temperature is going to drop, right? You're going to get this convective cooling, which cools down the edges of the block. That's going to create a temperature non-uniformity inside of the block. So the temperature of the edges will be lower than the temperature at the center. Fourier's law is going to kick into action and say, hey, we've got a temperature gradient. Start kicking thermal energy away from the center of the block towards the edges to equalize it. And in response, you're going to start to dissipate energy from the center of the block out towards the edges and away by convection. But throughout this whole process, the surface temperature is going to decrease, okay? Which means that this change, right, the difference between the surface temperature and the surrounding air is going to get smaller and smaller and smaller. So the convective heat rate is also going to get smaller and smaller and smaller. So the whole process is going to get slower, which is why it takes a lot longer to cool something that's only, slightly warmer than the surrounding air. Like the temperature of that's going to decrease much more slowly than it would if you put something that's red hot out in a room. Okay, so we've got one quick trivial little example, and then we're done. So our example here is just to prove to ourselves why this linear temperature distribution that we've assumed for steady heat transfer works. So let's assume that we have, right, some wall, okay? We have a wall with conductivity K. My K's are really not turning out great. And what we want to find here, let's say that one side of the wall is at some temperature T1, the other's at T2, and we want to find the temperature inside of the wall. That is the temperature along X. If this is our X, this is our Y. Okay. Our assumptions here are that the temperature only varies on X. So this is a one-dimensional problem. That we're operating at steady state, and that we have no heat generation inside of the wall. Okay, so there's literally just a passive wall with constant temperatures inside and out. So the solution here starts with our governing equation, which, if we wrote the whole thing out, right, would be rho c dt dt equal to grad squared t plus q prime. But because we've made these assumptions 1, 2, 3, we can cancel terms out. So the fact that it's 1d means that this just turns into x of t, and then steady state. So this is due to 1. This goes to 0 as a result of 2, and this goes to 0 as a result of assumption 3. So our heat equation just turns into, this is supposed to have a k, just turns into k partial x of t is equal to 0. Squared. Which is pretty trivial to solve, really. If we integrate twice, okay, we end up with t is equal to c1 x plus c2. All right? So now if we apply those known temperatures at the inside of the wall and the outside of the wall, that is, if we say that this wall is has a thickness of L, then we know that T equals T1 at x equals 0, okay, which is our first boundary condition. Plugging in x equals 0, we end up with T1 equal to C2. Okay. We also know that T equals T2 at X equals L. So plugging that into our, I should say this is our general solution. Okay, we're finding these particular one that if we plug in X equals L, we end up with T is equal to C1 times L plus T1, just equal T2. If we solve for C1, we'll get C1 is equal to just T2 minus T1 over L plus, yep. And so our specific solution here, if we plug in C1 and C2 now, just becomes T2 minus T1 over L times X plus T1. So the only thing important to note about this is that this just describes, if you have X and you have temperature, that whatever your T1 and T2 are, this describes a linear gradient between them. Okay, so in the previous examples, where for steady conduction, we assumed a linear temperature distribution, that's theoretically consistent. All right? If you don't have time derivatives and you don't have heat generation, the temperature is always going to strike a linear distribution as the equilibrium. So, all right. Thanks, guys. The homework number 2 will be posted shortly. I'm wrapping up some formatting on that. I'll see you guys on Monday.